Okay, the introduction to integration by substitution. Here's my approach to it. Okay, so we're going to do a non-definite, an indefinite integral of x minus 5 to the fourth. Now, if I'm trying to find the antiderivative, the indefinite integral of that, I can probably, and you may also probably be able to get that one right without doing any substitution technique. But I'm going to do that, and then I'm going to do it by substitution to show you how that works. So, if I've got something to the fourth, probably the antiderivative is going to be that something to the fifth, and divide by 5. Plus c. Now, to check, I would take the derivative of this. So now I'm doing a check. And so I take the derivative of this, and the derivative of 1/5 times x minus 5 to the fifth plus c dx. I take the derivative, the 1/5 times something, that just hangs there because it's times it. If it was plus, I wouldn't, but it's there. This to the fifth, we'd take the 5 down times x minus 5 to the fourth times the derivative of the inside, but that happens to be 1, so the chain rule doesn't produce anything that messes things up here. And the derivative of the constant that's added is 0. The 1/5s cancel, and I get x minus 5 to the fourth times 1, which is just what we wanted. So this is the correct antiderivative. Now let's get it doing substitution. Now what's making this a little hard to think about is that x minus 5. So we let u equal x minus 5. So if I take the derivative of this, du with respect to x, I get 1. But this is a small change in u, small change in x, so I can multiply both sides by the small change in x. So often I'll just write that on this side instead of writing it du dx. I'll just go right here and say the derivative of this is 1 dx. And 1 dx, so du and dx are the same. So if I want to do a substitution, I need to make a substitution for this whole thing and for that piece. And now I have the things to do that. So I'm doing the antiderivative, the integral, the area under this curve, of x minus 5, which I called u to the fourth, and dx is 1 dx is du, so they're the same. And to integrate that, we know the antiderivative is just 1/5 u to the fifth plus c. But I made up the u, so I need to take it back to x's, and so it'd be 1/5. And what did I make u be? X minus 5 to the fifth plus c. So I got the same answer. Okay? Well, that seems silly. We didn't need to do that because we did it in our head. Well, let's do another one that we probably could do in our head. The antiderivative, or the integral of sine of 5x minus 2. Well, what's making this a little messy is this stuff inside. So I'm going to let u equal the 5x minus 2. So taking the derivative, I'm going to get du on this side, and on this side I'm going to get 5 dx. So if I solve for dx by dividing both sides by 5, I get du divided by 5. So now I have something to put in place of this, u, and I have something to put in place of the dx. So doing my substitution, I have sine of u, and dx becomes du over 5. Well, over 5 is like 1/5, so I can pull out the 1/5, because constants pull out of integrals, and I have sine of u du, and I think I know the integral of sine of u. It's negative cosine u, if the variable is u, and it's times 1/5 plus c. But I'm in u, so I need to go back to x's, so I'm going to replace u with 5x plus minus 2. So I got 1/5, and the minus can be put on that. Cosine of u, which is 5x minus 2 plus the c. And that should be the antiderivative of this. To check, I would take the derivative of this. The derivative of negative 1/5 times something stays the negative 1/5. The derivative of cosine is sine. Negative cosine is sine, so I better change that to plus sine of 5x minus 2. Chain rule says times the derivative of the inside times 5, and the derivative of constant is 0. So the 1/5 cancel the 5, and I get sine of 5x minus 2, which is what I was trying to find the antiderivative, so it checks. This is the correct antiderivative. Okay, so now we're going to go to a little bit trickier one. Let's do this one. 2x squared over 1 plus x to the 6th. And I choose this one because it's hard to know what to let u be. And that's why I've chosen this one. Addition in the denominator is not fun, so some people will let u be 1 plus x to the 6th. So du would be, derivative of 1 would be 0, derivative of x to 6 is 6x to the 5th dx. Solving for the dx, I divide by both sides by 6x to the 5th. Making my substitutions, I would get the integral. I didn't have something for the 2x squared, so I'm going to leave that a little bit. And in the denominator, 1 plus x to the 6th is what I called u. And what I found out dx would be, if that was u, dx would be du over 6x to the 5th. Well, the 2 over the 6 isn't a problem. That could be pulled out, 1/3. But I would still have the u in the denominator, and I would have, the x squared would cancel there, and I'd have x to the 3rd here, and a 1 and a du. Well, if I'm integrating with respect to u, I don't want to mix, so I'd have to convert x to the 3rd into u's. And I could do that up here. I could subtract 1 from both sides, and u minus 1 would be x to the 6th. And to get x to the 3rd, I take both sides to the 1/2 power, square root of both sides. And that would change this to x to the 3rd, and it would be, this could be replaced 1 over u times the square root of u minus 1. But that doesn't look like anything I know how to do right now. So I might try something else. Maybe I should have let u be 2x squared in the numerator. Well, then du would be 4x dx divided by the 4x, and I would get du over 4x is dx. And the integral would be u over 1 plus, now I'm going to have to figure out what x to the 6th is. So I could divide by 2, and I'd get u over 2 equals x squared. And to get x to the 6th, I'd have to take both sides to the 3rd. And I would get u to the 3rd over 8. D, and the dx would be du over 4x. So I'd have to solve for x in here, so divide by 2 and then take the square root. So the x would be the square root of u divided by 2, and this is getting worse. So what can I do? Well, I haven't picked the right substitution yet. This is where it gets a little tricky, and this is what you got to get better at, and this takes practice. Addition in the denominator is tough, or subtraction in the denominator. Do we have any antiderivatives of anything that end up with 1 plus something in x, something in the denominator? And if you're thinking of 1 over 1 plus x squared, which is the derivative of arc tangent x, you're in the right ballpark. What would have to be here for this to be something squared? Well, x to the 6th is x to the 3rd squared. So that means I should probably let u equal x to the 3rd. Therefore, du would be 3x squared dx. And this would become the integral. Don't have something for the 2x squared. The denominator would become 1 plus u squared. U squared would be x to the 6th. And dx is du, I didn't finish solving for it, divide by the 3x squared. And, oh, sweetness here, the x squareds cancel. And therefore, I don't have any x's left. I've got something that's looking like the derivative of arctangent if I factor out the 2/3. So I got 2 over 3, that's in the numerator, that's in the denominator, antiderivative of 1 over 1 plus u squared du. That looks like the arc tangent of u. The derivative of that looks like that. We have the 2/3 plus c. Now we need to take it clear back to x's, so we got 2/3 arc tangent, and u we said was x to the third plus c. Let's check. So we have, let's take the derivative. So 2/3 would stay. The derivative of arctangent is 1 over 1 plus whatever's in the arctangent squared times the derivative of the inside, which is 3x squared, and the derivative of the constant, 0. This 3 cancels this, and I end up with 2 times 1 times x squared over 1 plus x cubed quantity squared, which is x to the 6th, which is what I was trying to get the antiderivative to. So this is the correct answer. All right. Now I'm going to discuss a little bit about the difference between an indefinite integral and a definite integral. For instance, what if it was the integral of sine of 5x minus 2, but find the area under this curve between, say, 0 and 1. Okay, so the x is going to be 0, and then it's going to be 1. We're going to put in 1, and then we're going to put in 0 into the antiderivative. But if we make the substitution, we get to this. So if the limits were 0 and 1, and we change to u, because this, changing that to a u, the sign of the variable, that curve looks different than the sign of 5x minus 2. So the limits have to change to match being in respect to u. So if the x limit was 0, if I put 0 into this substitution formula I have, 0 times 5 minus 2 is minus 2. U would be minus 2 if x were 0. And if x were 1, 5 minus 2 is 3. So this would be what happens if I change from the variable x to the variable u. I have to change my limits of integration. And then if I went ahead and solved this, minus 2 to 3, and I got this for the antiderivative, I'd be evaluating that from minus 2 to 3. There wouldn't be a c because I'm doing a definite integral, so I don't have this, but I would get, I'm going to put the minus in front of the fifth, so I got minus 1/5, plug into the cosine of u, a 3, cosine of 3, and then we do minus a minus 1/5, which would be plus 1/5, cosine of minus 2. Now I'm going to pull in the calculator here and figure out what that is in decimal. This would be an exact value, and if I asked for exact value, that's probably where you'd stop. But I'm going to bring out the calculator, and I'm going to figure out what that is. So I'm going to go on y equals clear. I'm going to quit, type in negative 1/5. Negative 0.2, that's 1/5. Cosine 3 plus 0.2 cosine negative 2. And I get 0.114769, whatever. Okay? Let's remember that. 0.114769. Anyway, that's an approximate answer, not exact. This is an exact answer. That's an approximate. Now, I could have gotten that approximate answer easily with the calculator by just going to y equal and typing in sine of 5x minus 2 and going second, calculate the area under that curve. Well, I got something funny here. Let's go zoom 4. Calculate the area under that curve from 0, enter, to 1, enter, and it says that area, some of it's negative, some of it's positive, totals 1.1147691. Same answer as we got there. But that's the exact answer. Now, what if we converted back to x's? Well, then the limits would go back to what the x limits are, which were 0 and 1. And so then I would have minus 1/5. Put in 1 into here, so cosine of 5 times 1 minus 2 minus a minus 1/5 plus 1/5 cosine, and I would put in the 0, which would be 5 times 0 minus 2, but 5 times 1 minus 2 is 3, what we had before. And 5 times 0 minus 2 is minus 2, and we'd get the same answer. So the point of this is, when you switch to u, the limits have to change. And as long as you're in u, that's those limits. If you change back to x, then you go change back to your old limits. So when you're doing this problem, a definite integral, and you do a u substitution, once you change the limits for the u, you don't have to go back to x. If you are doing this problem and you don't want to figure out what the limits are, you could just say, oh, I don't know what it is, and I don't know what it is. Keep working here, I don't know what it is, I don't know what it is. Get down to here, I don't know what it is, I don't know what it is. Go back to the x's. Oh, now I do. They're back to 0 and 1, and I could have avoided figuring out the limits for u just by skipping that and getting back to x and then do the limits. So you got a choice there. But please do not write, all right, I got this into u, and write 0 to 1 of sine of u du. No, over 5. No, because that's not the limits for u. These should be I don't knows and I don't knows if you don't want to figure out what the limits are with u. Okay. A couple of trickier ones. Let's do this one. The antiderivative, or the integral of sine of ln of x over x dx. What don't we like? Well, that ln of x in there doesn't look so good. Doing a u substitution for the whole thing doesn't do any good, because then we'd have to do the derivative of that. But let's just let u equal ln x. We could consider letting it be sine of ln of x, but let's see what happens here. So du, we have to get something to substitute for dx, so I got to take the derivative. And the derivative of ln x is 1 over x dx. Now, where does this x go? Well, we have to multiply both sides by x to get it out of there. So dx equals x du. And some of you might be thinking ahead and saying, when I replace dx with x du, the x on this is going to cancel here. But let's see that happen here. This would turn into the sine of u. Didn't do anything for the x. And dx becomes x du, and sweetness. And we have the antiderivative of sine of u du, and the antiderivative of sine is negative cosine u plus c, and going back to x's, ln x plus c. A check. Take the derivative of this, so the derivative of negative cosine is sine, leaving the inside alone, times the derivative of the inside, which is 1 over x, and the derivative of constant is 0, and so we get sine of ln of x divided by x, what we started with. The thing you want to notice here is when you take the derivative of ln, we get stuff in the denominator which shows up in the numerator, whereas most of the time it doesn't. Let's go here to this one. When we let it be x to the third, it ends up in the denominator, du over 3x squared. The derivative of that stuff ends in the denominator. Usually, ln is one that puts the x back into the numerator. Okay, another one. Let's see here. How about this one? Integral of x e to the negative x squared over 5. If you're looking at that and thinking, yeah, maybe that should be u, you are correct. So the derivative of u would equal the derivative of this, so that's negative 1/5, hangs out, and the derivative of x squared is 2x dx. So to solve for dx, we multiply by a 5, we divide by negative 2x du, and we make our substitution. We get the integral. You notice this x ends up in the denominator. We had one in the numerator. Things are going to happen nicely. We got x. We have e to what we called u, and we have dx, which is 5 over negative 2x du, and sweetness. This is a constant, that's time stuff, so it pulls out. 5 over negative 2 integral of e to the u du. We know that is e to the u times negative 5 halves plus c. But getting back to x's, it's negative 5 halves e to the negative x squared over 5 plus c. And finally, the last one I'm going to do here is the antiderivative of x over x plus 1 dx. And the first thing students love to do is try to make this into two fractions. If it was x plus 1 over x, you could split that to x over x minus or plus 1 over x. And then integrate 1 and integrate 1 over x, and you would be fine. Find the antiderivatives. But you can't split it when the sum is in the denominator. You can try a bunch of different things, but the easiest is think, okay, let's just let u be x plus 1. The derivative of this side, du. The derivative of this side, dx. So du equals dx. That's pretty simple. So we get the integral of, oh, we don't have anything for x. Let's leave that x. That we decided was u. And we have dx, which is also du. Huh. What are we going to do? We got x's and u's. What is x equal to? Oh, subtract 1. X is u minus 1. Oh, the subtraction is in the numerator. Well, that's fine because it can be split up then. And we get the integral of u over u minus 1 over u. Both of these are divided by u. Again, you can split when the addition or subtraction is in the numerator, and it's a single thing, but not when the addition is in the denominator. So this is the antiderivative or integral of 1 plus 1, or minus 1 over u du. The antiderivative of 1 would be u, because we're doing it with respect to u. And the antiderivative of 1 over u is ln, absolute value of u. Changing back to x's, it's x plus 1 minus ln, absolute value of x plus 1 plus c. If I wanted to do a check, the derivative of x is 1. The derivative of 1 is 0. Minus the derivative of ln of something is 1 over the something. And the derivative of c is 0. Oh, wait a minute. This doesn't look like that. What if we get a common denominator? See, this has got x plus 1. We better make this x plus 1 over x plus 1. That's 1. So we get x plus 1 minus 1. X plus 1 minus 1. That's just x over x plus, we got it.